yeah, I mentioned global workspace, but there are many other like theories: recurrent processing, higher order theory, attention schema theory, and so on. And but then we need to think what it means to implement these things, and then see what happens if we actually implement them. So,
Désolé, very, very désolé.
okay, yeah, yeah, the voice sounded familiar. Yeah. Okay, so this is one direction, and so as I said, we work in this direction as well. And then also recently, or I think it's already like 2 years ago, maybe I should try to remove this one. Oh, I cannot do it. But anyway, so but there's a like big sort of review paper by Butling et al. And I was a co-author of this paper. And so in that group, we listed potential functions of consciousness based on these theories: recurrent processing theory, global workspace theory, and so on. And so no, we don't know, or nobody knows whether implementing these will give rise to conscious AI. But at least this is a useful thing to know, and then we can use these criteria to see whether certain AI systems have some aspect, some functional aspect of consciousness. But of course, we didn't know whether actually, like a lot of current AI systems have these functions, and but it's hard to say whether they have conscious experience or not. Okay, so then we have to ask the second question. So if AI systems have recurrent processing or global workspace, uh, yeah. So we want to ask whether they are actually conscious, and well, we don't know, but also one thing we should recognize is it's also hard to tell whether uh, well, um, whether a certain system has a global workspace or not. So yeah, I will come back to this point later. But the idea is if you have kind of randomly connected neural network, it's hard to say whether it's doing the recurrent processing or global workspace. So it's kind of messy. So we need some sort of mathematical sort of criterion to evaluate whether certain systems have these properties. Okay, so then I also want to introduce the concept of universality. So, so as I said, it's difficult to judge whether an AI system has certain property, and so I took this table from this review paper, and so but it's saying that for all of these theories, it's basically difficult to determine whether the system has this key property. So yeah, because it's usually a kind of high level concept. So we can yeah. So if we from an external viewpoint, if we develop some system with attention schema or global workspace, it's an interpretation. So we have like external interpretation of the system, but if we are given a kind of random dynamical system, unless we mathematically precisely define those concepts, it's hard to tell whether they have those properties or not. So yeah, so in a sense, most of the current theories of consciousness do not have this ability to make prediction about the existence of experience inside, AI or aliens. So yeah, but I think so. We need to develop more universal theory. I'm proposing that theories of consciousness should have this universality. So I defined universality as following. So it's the ability of a theory to determine whether a given dynamical system is conscious, irrespective of its origin or composition. So that's the idea. So Yeah, and does it make sense? Yeah. Okay. Great. Great. Yeah. Yeah. So, and okay. I don't know if this makes sense. Okay, so but the point of developing such a universal theory is that once we have a theory, we can use the theory to make um, an inference about the existence of conscious experience. Now, of course, we cannot know for sure whether you know like aliens have consciousness or AI has consciousness, but yeah, but but if we accept some theory to be true, then at least according to this theory, this has consciousness, this doesn't have consciousness. So that we want a, a theory to have this kind of a universal property. So that's my argument. And yeah, but then even if we have a universal theory of consciousness, you cannot like really know whether AI has consciousness, right? But but my point is actually like a lot of things in this universe are we just don't know. We know for a lot of things we are actually making a guess, and so I wanted to give an example, but I don't know. Yeah, so no, maybe we all believe Australia exists and it's in southern hemisphere, but it's a theory, right? So, but we can sort of predict like seasons are opposite to the northern hemisphere, no, based on our theory of how the this Earth, no, is you know straighted. But maybe another example is the core of the Earth. Yeah, so yeah, so we all assume that there's a the core of the Earth is made of some sort of iron, and we feel like it's a fact, but but nobody actually went there and then took a sample from there. So we it's a theoretical inference, but we trust our theories of physics, and so based on like all the measurements and experiments we can do on the surface of the Earth, we make an inference. But we we have a lot of confidence in our understanding of this scale of conscious physics. So in that sense, it's not so strange even if we cannot directly observe the core. Uh, and also, I'm often impressed by people discovering exoplanets, and of course, we cannot go there and actually check whether there's water or something, but we based on like a lot of observations and sort of applying the physics we know, but we make inferences about size and composition of exoplanets. So in that sense, like consciousness could be similar. So even if we cannot go inside an AI and then see what kind of qualia they have, if we have a universal theory, like we can make a reasonable guess about the presence of qualia in AI. So that's the idea. Okay, I'll skip this and okay, and but one important thing is that when we think about a theory of consciousness, uh, we want to also have this kind of we want to use intrinsic properties of a physical system as an indication of consciousness, or to characterize the type of conscious experience happening inside some system. So the idea is it's a little bit inspired by integrated information theory type of thing, but usually, like neuroscientists try to understand what each neuron represents by looking at the relationship between the stimulus, like presenting someone image of an apple, and then you might find neurons responding to apples or oranges or red and so on. So, but this comes from like a extrinsic viewpoint. So the scientist is interpreting the meaning of the neurons, but but for neurons, they can only see other neurons. So and then they are not painted in red or other colors, but the meaning of this color red must come from its relationship to other neurons, or so it needs to be all determined in terms of intrinsic property of the network. So that's the kind of desired property when we try to establish a universal theory of consciousness. Yeah. So that's the idea, and from now I'm going to talk about qualia. So everyone is familiar with qualia. You all have some qualia, yes? Yeah. Sometimes people come to me and
No, I don't know what's qualia.
oh, okay, great.
You teach me.
Okay, yeah. So qualia are qualia refers to subjective kind of aspect of consciousness. So it's often characterized like redness of red. So when we see something red, it's not like we just process red, but somehow it's subjectively felt like kind of special texture or some color and things like that. So, but it's a little bit unclear. So some philosophers argue maybe qualia are not well defined, and because it's difficult to like really talk about this subjective experience. But so but often like people use color and also like pain as an example of qualia. But but we all have some,
It's really the quality of this subjective experience.
Yeah, this qualitative aspect. But
how it feels like.
Yeah, exactly. Yeah. So but I don't know. It's actually a controversial concept because when we try to analyze it, it's difficult. But on the other hand, everything we experience is composed of like all kind of qualia, right? So when we see people and there are different features, but it seems like we don't so interpret information, but instead of we directly feel the consequence or output of neural networks as some sort of experience. So that's the gist. Maybe we can discuss this further. Okay, and so I want to introduce this interesting experiment from Muriganka's third lab around year 2000. So when we think about qualia, it seems like an impossible thing to study. But their group, it seems almost impossible, especially in animals. But they have like a very interesting operation to rewire the retinal input to the auditory cortex. So this is what this diagram is describing. But the interesting thing is they rewired only half of the visual field to the auditory cortex, and then the other half went to the normal visual cortex. So, but the interesting thing is, actually, rewired auditory cortex responds like visual cortex. Maybe not too surprising, right? So they receive visual input, and then they develop the typical orientation selectivity, and also connectivity patterns similar to the visual cortex. So in the visual cortex, the neurons responding to similar orientations tend to be connected together through horizontal connections, and that kind of structure doesn't exist in the normal auditory cortex, but that was also observed in this rewired auditory cortex. So that's what this figure is showing, and yeah. So the interesting thing is, okay. So first, this animal was trained to report whether they received light input to the retina or sound. So basically, they had to discriminate sound versus flash of light, and using the intact part of the retina. And then after the training is done, then they flash the light on the rewired part of the retina. So the interesting question is whether the animal responded as though it heard the flash or saw the flash. So you can ask this question, right? So, and the answer, what do you think? You know this experiment already? Yeah. So yeah, the answer was that the animal responded to the stimulus as light. So what this experiment suggests is that so basically this kind of local connectivity reflecting the sort of peripheral input seems to contribute to the subjective experience. So now, of course, we cannot directly experience animals' qualia, but I think it suggests that like local network structure shapes the type of experience we get. So it's an interesting question, and inspired by that. I don't know if you are familiar with the so-called integrated information theory of consciousness, and it's developed by Giulio Tononi, and it's been a very controversial theory, and some people really get angry when they hear the word IIT, but it's actually one of the, it might be one of almost like the only one theory that that is universal. So basically, with IIT, if you know all the mechanisms at the physical level, or maybe like at the neural level, you can tell whether a system has consciousness or not. But for practicality, it's almost impossible because it's computationally not really tractable, but also to compute this quantity called phi in this theory, you need to know all the weights of synapses, and so it seems like a impossible theory to apply to real things. But the main concept is really interesting. So explaining everything takes time, but according to this theory called IIT, qualia are determined by the shape of information structure. So so in a way, like they describe it as this kind of constellation in high dimensional space, and then we expect that we get the different kind of structure for visual versus auditory, like especially like for this rewiring ferret experiments. Like if we could have like all these synaptic connectivities in the visual cortex and auditory cortex, and also rewire the auditory cortex, we should be able to identify the sort of structure that corresponds to visual qualia or auditory qualia. So that's the motivation. And so if we can sort of take anatomy of auditory cortex and visual cortex, and then maybe with some sort of functional calcium imaging, you might be able to get all the connectivities in these tissues. And then you can apply IIT, and you get very complex information structure. And then eventually, you might be able to find the correspondence between, information structure for auditory cortex and information structure for visual cortex, and then there might be some sort of, correspondence with visual qualia versus auditory qualia. Yeah, but then this is very hard, right? So it's getting kind of feasible to detect all the connections, but it's hard to know all the weights. And also IIT is very hard to compute. We've been trying to compute IIT, but even with 10 neurons, it gets too hard. Yeah, and then so what we have been doing is to do this with artificial neural networks. So instead of using actual brain, we can train a lot of neural networks for sound or images to create kind of virtual auditory cortex and virtual visual cortex. And then so that kind of solves this anatomy problem. And sorry. And then we also want to replace this IIT part. Yeah, because this computation about IIT is hard, and this is a little bit too specific to IIT, but one way to work on IIT is to sort of use some sort of like a mathematical approximation to compute this. But another approach we're taking is conceptual. So according to IIT, this structure of the network determines the type of qualia. But we don't use IIT to compute this. So let me. Yeah, so basically, we trained like a lot of neural networks, and then with different the initial conditions, and then each neural network is characterized by some weights. And so what we wanted to do was to develop a meta neural network to classify all these different neural networks in terms of on what data they were trained on. And so this is we're just taking the concept of IIT. And so, but also I wanted to maybe I assume many of you might be already familiar with a lot of like neural network stuff. But typically, like people use autoencoder, variational autoencoder to compress some information and then reconstruct. So but through this kind of bottleneck. So with this kind of typical autoencoder arrangement, you have a representation of images in the latent space. And so, but what we are doing is more like this. So we train a lot of neural networks, and then we can encode neural networks and then reconstruct. So that way, we can reconstruct or we can represent networks. So it might be a little bit confusing, but it's a useful thing to do because so imagine that like some networks are trained on images, some networks are trained on sound, and then you want to know whether they have kind of distinct properties in this meta latent space. Yeah.
It's not clear from the previous slide. The classification is based on features that are extracted from the network, or the classification is based on the data on which the network was trained?
For this classification, basically classification is done based on this weight structure, just the weight, without using the data set. Yeah.
How do you deal with the permutation problem of if you retrain a network, the permutation of weights can be very different?
Yeah.
Even though it's trained on the same data, you just sort it before you encode it, or you sort your weights?
Yeah, very good question. yeah, actually, like we have to do a little trick to deal with that. So yeah, actually, like instead of open, well, actually, we use just a single layer encoder, and then you get I think it's like there are 16 units in the middle, and then so each vector is a filter for the image, and then we first encoded like we use one meta autoencoder for each unit, and then we use another one to deal with the this permutation. So then we put So there's a sorting for this like first meta encoder. So yeah, so then we put everything together in it, and then so we actually use these two meta autoencoders to deal with permutation problem. Okay, so then what happened was, so for vision tasks, we had something like 10 or 1, 2, 3, 4, 5, 6, 7, 8, yeah, 10 vision tasks and then 10 auditory tasks. And so basically, all the networks we trained were separated by modality. So it seems the weight structure captures the difference between vision versus audition, and so this is a Disney of the meta latent space, and then this is the confusion matrix for predicting individual stimulus, individual category of the data set. This is like airplane, bicycle, and so on. Yeah, so of course, it's not perfect, but there seems to be like also some kind of bright diagonal. So especially for the sound, maybe they are more distinct. Yeah, but this suggests that the internal structure has some sort of like a correspondence with the some properties of the training data set. Okay. So does this make sense so far? Or too confusing? Okay. How am I doing? Okay, perfect. Okay, then from here, I'm going to talk something a little bit more speculative. So I want to propose this qualia equivariance hypothesis. So these are my main claims. So the qualia are fundamentally determined by the equivariance properties of neural networks that process sensory information. I will explain what this means in a second. And then each sensory modality, like vision, audition, it could be tactile, is associated with distinct equivariance patterns inherent to the neural networks. But maybe I should explain what equivariance means. So I took this nice image from this link. So you might know the concept already, but it's kind of like it's very similar to invariance. Invariance is a special case of equivariance. So maybe like when you do computer vision, you might do sort of a pose estimation type of thing. So this F is a neural network, and so when you have a person like this, and then you get the key points. So that's what we all do with typical computer vision, right? But then, but if you sort of horizontally translate the input image through this transformation, and then apply the same neural network, but you get something similar. And so basically, you get the same result if you apply this neural network and then translate, or if you translate and then put it to the same neural network. And then this neural network is said to be equivariant with regard to this transformation. So that's the concept. And also, like here, but usually, like this kind of transformation is described in terms of some type of group, like in mathematics. So, and there are many types of groups, but yeah, but that's the idea. But for example, for vision, it's normal to we expect this kind of invariance or equivariance for horizontal translation, and also like objects don't change by rotation, but maybe 2 and 5 could be different objects if you flip like or rotate 180 degrees. So there might be some limit, but if you do but if you take something like this for audition, and then let's say we have like time frequency, power spectrum for auditory input, and then maybe for visual images, if we sort of rotate or if we move things up and down, we recognize them as the same object for vision, but if we do similar thing for sound, we recognize them as completely different things. So in that sense, for different modalities, there seems to be different kind of equivariances. So that's the intuition. And also, like in the meta network experiment I showed you earlier, there must be some sort of property captured by the neural networks after training. So our hypothesis is that this some sort of equivariances might be learned by the network, and then they became more like visual or auditory. So that's the idea. Yeah. So but this is more like formal definition, and so I'm kind of writing this more mathematically, but all this is saying is we can go this and this and they are the same. So you can apply neural network first and then translate or transform, or you can transform and then apply neural network. And if they are the same, they are called this G equivariant. So this network is equivariant. With regard to this group G. So that's the idea. And okay, so this is like more like formal statement of the hypothesis. So but basically here this is basically the same thing as the definition of equivariance. So if something is equivariant, then that basically this group G characterizes the type of qualia the system is experiencing. And of course, it's hard to say whether they are experiencing something, but at least we can say whether a certain neural network is more similar to visual processing or auditory processing. So this is more explicit statement, and so maybe you might have heard of the title called "What It Is Like to Be a Bat." So the question is, so when a bat is doing echolocation, so they are understanding the space through the sound or air pressure. So in a way, it's like auditory processing, but functionally what they are achieving might be more like seeing. So then it's kind of but philosophically it seems like an impossible question to answer. But maybe if we do this on a bat, we may be able to say, oh, okay, the neural network is more like visual cortex, something like that. So yeah, that's the kind of thing we could do. But another thing I wanted to say is that maybe here I presented equivariance as kind of as a kind of mathematical concept, but actually in the actual neural network, probably this kind of symmetry is not perfect. So, for example, we can think about color, and then color is circular. So then we might associate some sort of like a rotation related group as a corresponding equivariance, but there seems to be also some sort of there might be some symmetry might be partially broken, because if everything's symmetric, there's no distinction between red and blue, but this might be there might be some sort of imperfection which makes like specific experience more like red or blue, but this part is more speculative. Okay, and then I listed potentially relevant type of group. So like there's something called Euclidean group, and for vision and for audition. There are some groups, and there might be some sort of like for like musical things. There might be this kind of cyclic symmetry, and for body, for like somatic sensation, like you might have a lot of degrees of freedom, and then they may have some corresponding type of group and so on. But this these are all like very fast approximation, but maybe in reality we might have to think about more complex version. But this is kind of implication of my claim. And also the interesting thing is this is not very common in neuroscience, but in AI research, especially in the context of sort of mechanistic interpretability or geometric deep learning, there's an interest to sort of quantify to what extent a neural network is equivariant. For example, this paper kind of computed this degree of equivariance in terms of this G empirical equivariance deviation. So basically, as I said, for a network to be equivariant, these two quantities need to be identical, and then this m is basically the distance between them. So if the difference between these two, like gx and so G first transformation and neural network versus neural network and then transformation. So if their difference is small, it's likely to be more equivariant. And so, but computationally, you can compute this for many types of transformations, and also like you need to test this over a big data space. But then you can quantify to what extent a neural network deviates from equivariance about G. So that's the general idea. And so this paper did that, and so this is like a very simple example. So this is the original one, and then they sort of applied various rotations, and then you can compare how the average of these change from the original. So that way, if they are very similar, that's equivalent to this kind of rotation. So that's the idea. So at least you get the sense that it's in principle possible to compute something like this. But of course, the thing is there are like many kind of transformations described as a kind of group, And so that's the kind of difficult thing to do in practice. And also, like, I want to talk a little bit about Lie group, Lie algebra, and so on, because that's very relevant. And but explaining everything about Lie group might be tricky. So I was watching this like very introductory YouTube. So like, if you're interested, that's good. Yeah, and so I skip everything about Lie group in a way, but basically, Lie group is a kind of group that's also a manifold, and then you can consider. I don't know if it makes sense to you, but actually, like, you have to, maybe watch some YouTube or read some intro textbook. But then you consider an algebra defined over the tangent space. And then the interesting thing is, if you, so in this kind of mathematical framework, there's a concept called the derivative, and so that gives you that gives you a measure of equivariance. So I also find this kind of useful picture. Yeah, so like derivative is like you change something a little bit and then see how much things change. So in this case, so with Lie derivative, you sort of look at the kind of how vector changes in this tangent space by changing the input a little bit. So basically, you can consider this as the output of neural network. So you can see how much the final outcome changes depending on by like shifting the input in the original by the original group operation. So basically, if these these vectors are, let's say, the output of a neural network, and then if they are very different, they are not equivalent. But if they stay the constant, so if the Lie derivative is close to zero, then it's more equivariant. So there are like people who are applying this Lie derivative to compute kind of equivalence error, and then here they found some performance in ImageNet accuracy and this equivalence error. So if this value is lower, that means the network is more equivariant about this rotation, shear, and so on. And then the performance is better. So if a network learns the properties of the images, then they gain more equivariance for these transformations. So I think that's very promising and interesting. So I want to use this kind of method to also analyze the brain. So that's the idea. And I also have some further speculations. So like in conscious experience, we often talk about kind of compositionality. So like we have color, the shape, and so some things are sort of independently changed, but also there's some sort of hierarchical structure, right? So like face is kind of more holistic thing, but then inside the face you have eyes and so on, and then also like there's a whole thing and so on. So this kind of compositionality is a characteristic of conscious experience, but also like this kind of equivariances can be mathematically decomposed into sort of like elementary or sort of certain type of groups. So that way maybe we might be able to classify different types of qualia in terms of groups. And but I want to know what mathematicians think of this. And so in a way, so we may be able to characterize what kind of qualia aliens have in terms of groups, And so that would be a new way to think about consciousness. Okay, so these are the summary. So I propose a hypothesis that qualia are determined by equivariance. And then we also showed that there is some sort of intrinsic properties of a network that corresponds to the modality. And yeah, and then also my speculation is that different equivalence patterns correspond to different sensory modalities. Yeah, and then eventually we want to use this for the brain, and I think that would be a really exciting new direction of research. Yeah. Okay. Yeah, that's all. Thank you very much. Yeah.
Thank you.
Complaints.
Yes. So time for questions. Anybody?
Yeah.
Thank you.
Oh, Sylvie, we don't hear you.
For the slide, when it was a comparison when it rotates the number 5, and then
We don't hear you.
here. So you said that the averages can be different and can be the same. Could you please? I can model. Could you please give an interpretation? What does it mean if, for example, average representation bigger or smaller than the original figure?
Bigger or smaller?
Yeah. Let's start with bigger. So what happened if the rotation found that average is bigger than?
So big in terms of.
I mean, you have like two properties, right? The average from the rotation and from the 5, and you compare them. Did I understand correctly?
Yeah, but they are like this. So comparison is like this. So they are vectors. So you have one vector, original vector, and then you have kind of transformed vector. And so if the difference is small, and that means this network is equivariant to this transformation. So there's more equivariant. But if the difference is big, this network treats everything as different. So after transformation, for this network, there are different things. So so that's it.
Which difference?
Which difference?
Which difference is smaller generally? Because I mean, it should also rotate, no?
Actually.
It needs to rotate as well. Computer different. After you rotated the representation. If it's equivariant.
But here. I think here it could be just the difference. So like you take two vectors and then you compute the difference between them. So it could be just Euclidean distance, but you could use like
invariant.
Whether that's right. Yeah, that's a tricky thing because you have to think about the transformation in this latent space representation, and then there is some degrees of freedom in terms of what you could.
Can you turn the sound on? Because I think there's a question online. Sylvie, can you hear us? You had a question?
Can you hear me?
Yes, we hear you now.
Okay. Well, I hope I'm not interrupting. I can't really hear that well, but thank you so much for a good talk. My questions are manifold. Firstly, I really like the interdisciplinarity of what you're doing. I wondered a couple of small things. I disagreed a little bit about your assertion about the difference between sound and auditory information and visual information. I mean, I got your point that in visual information we have this sense of affine translations, so somehow the true image underlying what is being seen is the equivalence class modulo this affine shift. Right, but and you said it's not the same with audio information, but I disagree, right? I mean, if you play your favorite song and you tweak the dial a little bit and you push the auto tune up or whatever, you can still recognize that it's your favorite song. Likewise, if you go into the water, and someone played your favorite song, you would still recognize it. I mean, but maybe I take the point that these are happening there are different symmetry groups acting on these things. Another small point was that, you might want to think about projective groups, especially on the, obviously in terms of visual inputs, right? Because it's of course not really an affine thing at all, but it's like projective transformations. That's another thing I wanted to kind of add in. But I thought the main thing is I wanted to try to understand your definition of universality. Could we talk about that a little bit? So in your paper it says we define universality as the ability of a theory to determine whether a given dynamical system is conscious, irrespective of its origin or composition. So is the idea that, we need to kind of set our terms. So it's the idea that, within the universe is somehow inhabited by dynamical systems from your point of view. And some of these, or rather a theory of consciousness may or may not be universal. And universal is those theories of consciousness that in fact discriminate regardless of the origin or composition in your words of the dynamical system. So rather than you mean it should be applicable to any form of dynamical system, brain, AI. Right? I understand that, but you don't actually say that it should discriminate correctly. So I suppose your point is that you don't actually. You're rather agnostic about whether there is or is not a correct notion of consciousness.
Yeah, you're right. Yeah. So I don't assume that the universality requires correctness. So, but here, what I'm writing is, some people assume that consciousness happens only in the brain with biological neurons. But then it also needs to be defined. Yeah.
I mean, forgive me for playing devil's advocate. Aida knows me and knows that I'm a bit of a hopefully a polite qualia skeptic. I'm not really sure what qualia is, and I'm not really sure what consciousness is supposed to be. And I'm pretty sure I don't experience it. For me, I don't know what qualia is. I don't know what consciousness is, and and this is the key thing for me, I've no idea why they should be related.
Qualia may not be related for you.
Yeah. Yeah. Well, I mean, I just don't know what they are, so I don't know. And I know that I'm playing the devil's advocate a little bit here, but if you can forgive me for that. I really like the analysis of kind of, equivariance and group actions and quotients by group actions. But I don't understand what that has to do with us approaching universal and correct theories. And crucially, us coming to any kind of conclusion about whether there is a correct notion out there. Perhaps one more thing. I don't want to hog the time, but it struck me that this whole consciousness stuff is a bit like 90 years ago when they were thinking about what the notion of an algorithm was, right, in maths, and if something should be algorithmic, if something should be computable, if something should be kind of effective, what on earth should that mean? And the way that we resolved this was not by proving that the, quote unquote, God-given definition matched that of a Turing machine, or that it matched that of the recursive function, or that it matched that of the lambda calculus, but rather we have to be agnostic about whether there's any abstract notions, and we just note that these many theories happen to coincide. So my feeling is that what we should really search for is some kind of sense as to whether these different theories are ever going to coincide on notions of consciousness before we worry about whether they're correct. And maybe that is your point.
Yeah. Well, yeah, I think you really got what I wanted to say. So, so I think what I wanted was kind of method to get kind of like a quality of a function. So whether that really corresponds to qualia or not is unknown. But if we have a if the framework I proposed works, we can actually use this for sort of predicting whether a tissue of the brain is from the visual cortex or auditory cortex. So I want to see whether there's anything consistent across biological brain and artificial neural networks. And so that way, we get a method to analyze some qualitative intrinsic properties. So that's the real goal. And then eventually, we can, especially with biological brains, we should be able to test this idea by looking at the correspondences between the type of equivariances we find in the brain and what people report by, activating that network. Now, of course, it's going to be a little bit indirect way of sort of proving this concept, but I think it's still, this is not completely untestable. So there's a potential experiment and analysis to be done.
Well, and I think I understand why we're talking about qualia. If you're constraining your attention to group actions where there are finitely many, so somehow at the end of the day, you have finitely many things you want to talk about. Like, I don't quite know how to put that, but maybe there was some. I'm still not sure what qualia is supposed to be, but.
Yeah, it's a difficult question. I don't know how, if I have an answer, but
yeah, well, I just suspect that there is no answer, but more depressingly, there can be no answer. In the sense that it can never have a meaning because it's always got to factor through. We can never communicate more profoundly than discussing testable things.
May I ask a more trivial question? May I ask a much more trivial question? There's something wouldn't another hypothesis be that any structured data that generates anything like a neural network would probably be classifiable by the structure of the data, or there wouldn't have been any learning? So why would it be surprising that something as different in its structure as auditory and visual would, present different structure? Wouldn't we expect it even from basically anything that is not pure noise, anything that has any level of structure should present neural networks that have different structures?
Yeah, that's a great question. Actually, there's a weakness. Maybe my answer may not be directly addressing your question, but one real weakness of our current method to detect equivariances is if you use noise in the input, it looks like everything is equivalent because noise. If you put noise in, you get noise out, and then they are all similar. So,
but if you use pseudo-noise, I mean, if you use anything that does have structure, we just algorithmically create many classes, a tree of structures. So it does classify. So we would expect a neural network to learn some structures from it, and we would expect it, like the null hypothesis should be that they would group together. Why is it interesting to see that there is a difference? Because that should be evident. No?
Yeah, but I think it's interesting because they have different structures. So we want to find what kind of different structure networks learn, or what kind of different structures are in the data. So and then, of course, conceptually we know that there must be some structure, and then but we want to know what kind of structure there is. So that's the approach.
And the supposition is, or what you're trying to prove, is that there is a symmetry between the original signal and the structures. The
structure. Yeah, so structure tries to capture this symmetry in the original data. So because if everything's the same, this network should try to sort of treat all of these things the same. So actually there's a paper that connects this idea of information bottleneck in neural networks or information theory with equivariances. So that's one way to efficiently compress the data, because if there's anything redundant, you want to find that redundancy, and then that's structured. So this learning of invariances and equivariances come from the sort of efficiency or requirement of efficient compression.
Oh, sorry.
I wonder actually what degree structural behavior can be brought into correspondence, because that's usually the problem with all these emerging phenomena. The structure says one thing, and then the behavior goes out and does something complicated and wrong. I wonder in how far we're all convinced that looking at the structure of something allows us to understand the class of objects that we recognize. For instance, I'm thinking about the visual cortex, okay? All this theory, I vaguely remember from the 80s or something, fractals. And it taught us that basically the images we see, the two-dimensional images of the world, can be represented as the fixed points of a certain number of mappings. But this fixed point is iterated. And so essentially we should be able to find this structure of fixed point of mappings inside a neural network, which recognizes this object. The same thing for roughness, roughness, texture, etc. We should find corresponding operators, but we won't necessarily, because the behavior and of the object and the structure of the object maybe cannot be easily brought into correspondence. That's what I'm a bit worried about.
That's So can you repeat the last bit? The correspondence between structure and behavior.
Yeah, we have this thing on the one hand, and it's there physically, and we look at it, and that's a structure. And then we have the thing it does when we're alive, which is, in your language, generate qualia, for instance, in your particular and this can talk about them in certain ways.
So it's actually dynamics of...
Yeah, exactly. The dynamic behavior of the thing when it's alive or whatever. Yeah? And I'm not so sure that whether it's an emergent phenomenon, that the structure and the behavior can be put neatly into correspondence. Actually, a lot of philosophical theories say that we have a problem with this. We can call it emergent, whatever. It's not easy to actually do the action of bringing the structure and the behavior into correspondence.
Yeah, I'm not sure if I completely understood, but I got the impression, like, since you mentioned like fixed point and things like this. So in a way, like, structure is just one thing, but when you have like kind of recurrency in the network, you have to apply different functions 4 times, and that may make the processing more dynamic. And so here, like all the analysis I did was only for feed-forward simple neural networks. But when you have might become a little more complicated. Yeah.
So, basically, so I should say, it's a bit, it's jumbled, ramble. But yeah, this idea of reintroducing the temporal dynamics. I guess there's a quite striking similarity between this and what is proposed by Noether's theorem, that in a physical system, the equivariances of this system naturally correspond to some conservation law. I just wondered if has your thinking gone in this direction at all?
Yeah, interesting to find those things. Yeah, but I haven't done much about it. But I think you're exactly right. So that's a really thing, interesting thing to think about.
Have you?
David hasn't asked you this question.
Like, I was wondering, not sure I understood, but is it like equivariant is a requisite for quality?
Great question. Yeah, so somehow I feel like like really like pure equivariances do not exist in the brain or in neural networks, because there's a little bit of randomness and imperfection. So yeah, so um,
Because I was thinking that if you take identity network, it's equivalent to the whole group. And so you could attribute qualia to a network disconnected from the input to output one.
So I think we may have like special qualia for that. So yeah. So it's a hypothetical thing, but I think that's one kind of qualia.
Wouldn't that be the experience of being blind or deaf? No. Sorry.
But I don't assume that there should be perfect equivariances. Yeah, I think in actual qualia, equivariance is a little bit broken.
So I have a question about the symmetry breaking. You mentioned that maybe, so you have a certain type of symmetry in the visual and, depending on the sensory input type, but then when that symmetry within visual starts breaking, that is how you get blue versus red. I would say that blue versus red is more a feature than a bug. So I'm not sure if the symmetry breaking would be how you get that.
Yeah, so, but I think even for space, we have up and down, and so there must be a little bit of symmetry breaking. And
I completely agree that in a real neural network, biological or digital, there will be the equivariance is not going to be perfect, and that's why you have the measure that tells you like, are you a little bit off or way off? But can you help rephrase? You seem to agree.
Yeah, I had a very similar thought, which is, I guess the reason why equivariance is the relevant concept here as opposed to full equivariance is that you keep some semblance of the transformation that you made. So it's not that you're destroying any information about red versus blue or up versus down, right? Is this kind of what you're getting at? Like this is still represented after?
Yeah, I think red versus blue is a result of some other kind of difference rather than breaking the symmetry. So I'm just curious, what makes you think that the symmetry breaking within the visual cortex would let us see red versus blue? Like, how did you connect those?
Yeah, so actually, this came from another group of work called Qualia structure. So there's a like actually research grant called Qualia structure, and they are looking at kind of like so they try to understand whether the red one person sees is the same red other people see.
That I agree completely.
Yeah.
Yes.
Then they compared pairwise colors. So like the subjects had to sort of evaluate how different two colors are, and then basically you get sort of similarity metrics from each person, and then you can find kind of optimal way to align the similarity metrics, and then you get more or less perfect correspondences. So that means there is some asymmetry in this color space which can be captured, but otherwise so they are just aligning. So if they are completely symmetric, you get the similar structure, but then one person's red may not correspond to another person's red.
But you can actually go and dissect the human eye, and you can look at the pigment in the red cones. And actually, I think what you'll find is that, please excuse me for being politically incorrect, but most males and most females see different reds. There's a mutation, I think I have it, which allows me to see female reds. And so actually, the population does not see the same reds.
Actually, their team also looked at people with two cones, and then they found different structures. So in a sense.
Yeah, my own eyes don't see the same green. If I look at the same object, I see very different shade of green with my eyes. But can we generalize the delta that shifts the color perceived by different biological apparati to the notion of major wavelength difference detection?
No, you can't, because it's a three-color. Basically, the things which were very metamerically identical in one of these spaces will not be metamerically identical in the other space. And so actually, I don't think that there's a translatability between the qualia in one case and the other. They will never get superposed. That's my feeling on this. I used to be a member of the International Color Consortium. That's what I'm thinking of reasons. So people have to check that they will actually show the user when you do the video the impression they get, the quality they will generate. And this is a very important discussion for people like that, for Sony in particular. It's not abstract.
How do you interpret the fact that, anyway, I'm saying this intuitively because I don't have the scientific knowledge of it, but intuitively it is very hard for humans to read mirror text, while we can read upside text. Usually we can, within 2 seconds, adapt to upside down text. So how do you interpret that if, in effect, like there's a mathematical symmetry, good stuff within these, how come these are so different?
Oh, great, yeah. Yes, but I think for mirror images, probably the visual system doesn't have the equivariance for this kind of trans.
We can do it very easily for everything that is not text. As far as I know, you can correct me, you can test it immediately. If you were to see this slide like that, you would have a problem in reading it, but you will have no problem if this was inversed like that. And you can train yourself to read upside down within minutes.
With rotation, but this mirror flipped. Is different.
Because if they are mathematically not very far away from each other.
Actually, they're good.
But if I think one could come up with very plausible, though highly untestable, evolutionary kind of explanations for this. I mean, we don't have that many mirrors, whereas we're very good at moving our pieces of paper around or moving whatever it is. It's not writing, of course, going back that far, but I suppose that's quite testable. Whether faces, for example, symmetric. I suppose people have done that.
It has been done, and
just how well.
Yeah, and there's no problem. We have no problem of doing mirror images for everything that is not text.
Interesting.
Yeah.
Interesting.
No. Any symbolic system is not but any symbolic system, you can invent a new symbolic system. You will have a problem if it's written from the left to the right or from the right to the left. You will have a problem if it's from bottom to top or top to bottom, but you will not have a problem if you rotate.
It's weird because historically, texts were written from left to right or right to left. Think of hieroglyphs.
Yeah.
Whereas they're just.
You will have no. If the letters are not inverse, you will have no problems.
They were flipped mirror, and Egyptians are no.
To be clear, it's at the character levels that you will have an issue. If you write the character the same way, but you write the text from right to left, or from left to right, you will have no problem. It's just if the B has its side the other way around, that you will have a problem in identifying.
Hieroglyphs are fully flipped.
Discussion after we have 3 minutes left after we close the discussion. If there is one last quick question, we can take it, and then we move to La Montagne as usual.
So this already, my first question was, are you always strictly talking about equivariance if you talk about equivariance, but sometimes you talk to specific case invariance? Because I think sometimes you talk about. The key question is why are you focusing on exactly this property of neural activations? Because if you're focusing on other things, why would it be equivariance or invariance? That would kind of give you conscious.
Okay. So the question was why equivariance, or equivariance or invariance?
Do you use this exchangeably? Most of the time mean equivariant if you say equivariant and not invariant.
Well, yeah, I think depending on the context. So yeah, but I think I tend to say equivariance because just because it's more general. But other times, I have invariance in mind. And for the second question, actually, equivariance is not the only intrinsic property of a network. So, for example, you can think of graph properties. For example, centrality and things like that. They are also intrinsic to the network. So, and also, you could do topological data analysis and look at the global structure. So that's also intrinsic. So there are other things that might contribute to the qualitative aspect of a network or experience. So I'm aware of those, and yeah. So, but also another thing is here I'm focusing on the weight and connectivity, but also for practicality you can compute a lot of interesting intrinsic properties by sort of presenting inputs, and then analyze the kind of sort of patterns of representations in the latent space and things like that. So that's so there are other things, and I acknowledge that. So but here I'm just focusing on this very specific one.
All right. Thank you again.
Hello. Yes,